Hi, my name is Guillermo Fernandez Rodriguez, and today I'll be talking about the experiment 1. The goal of this experiment was to measure the outlet velocity of the water in a Marriott bottle given a constant pressure. With that in mind, we analyzed the rate of change of the water level and calculated the outlet velocity. The results obtained were that the outlet velocity was that of 1.0 plus minus 0.6 meters per second. Afterward, Torricelli's theorem was used to determine the theoretical velocity and compare it to the experimental value. At the end of the experimentation, we found out that our results were conclusive as expected value lied within the uncertainty of the measurements. Marriott's bottle is a device that delivers a constant rate of flow by keeping the pressure within the bottle constant. The bottle consists of a closed glass jar or a barrel, except for two openings, one at the top for inlet tube and one either at the top or the bottom of the bottle. As the inlet tube lets air inside, the pressure inside the bottle remains the same as the atmospheric pressure, therefore allowing the water to exit the bottle at constant speed, despite the variation of the water level. This is a direct application of Torricelli's theorem, as it models a specific case of Bernoulli's principle in which pressure inside the bottle and outside the container are considered to be the same. In this report, we will analyze the velocity of effusion of water and air within Marriott's bottle. To accomplish this task, we shall measure the rate of change in the level of water H over time. This will allow us to model, comprehend, and analyze the behavior of the pressure and its effects on the effusion speed, henceforth allowing us to have a better conception of physics involved. Our goal in this project was to comprehend in a practical way the mechanics and hydrodynamics involved in the Marriott bottle. This will help us develop a better understanding of the world that surrounds us. Furthermore, this experiment will be valuable for our performance as engineers, as it proves that although computations may seem perfect, even the most basic theorems may present uncertainties when translated to the actual world. To build this Marriott bottle, we established a theoretical framework in which we defined values and equations that would be useful during the experimentation. As equipment, we used a cylindrical bottle container. Here, we chose a 3-liter subtle bottle to take as long as possible when emptying the bottle. The atmospheric pressure tube. In this case, it was a metal straw with a 0.5 centimeter diameter. A drain tube. Here, we used a 10 centimeter long antibacterial health straw with a diameter of 0.5 centimeters. To seal the atmospheric tube to the cap of the bottle, we used putty and silicone glue. We used also a measuring tape to measure every 5 seconds water level. Also, we used an additional container, this to reduce the waste of water, and a stopwatch. To build this device, it was first required to empty the bottle and remove the tag. Then it was necessary to make a hole in the cap of the bottle to introduce the atmospheric pressure, which was sealed to the cap using silicone glue. Afterwards, the bottle was also perforated with a heated knife to introduce the drain tube. With the goal of taking measurements of the level of water, a measuring tape was placed along the bottle. To waste as little water as possible, a bucket of what was set on the lower end of the Marriott bottle in order to collect the exiting water. Well, here we have two pictures. In the first one, we can see the experimental setup. Number 1 represents the atmospheric pressure tube. Number 2, the seal. In this case, it was putty. 3 represents a measuring tape. 4 represents the whole bottle, and 5 represents the drain tube. By the other side, in the left picture, A represents the measurement of the area inside the bottle. D represents the diameter of the bottle. H represents the distance between the outlet of the bottle and the input of the air, and H represents the water level. Here we have the measurements H, D, and D. Each one represents a different part of the bottle. D represents the diameter of the exit bottle, D represents the diameter of the bottle, and H represents the distance between the exit hole and the input hole. Then we took the 5 times the measurement of the height every 5 seconds. This was to have a more accurate measurement of what we were doing. Then we measured the area and calculated the uncertainty of the measurements. Then we calculated the velocity corresponding to each value of time and average water. These values were calculated by doing the following. To calculate H, we obtained the average of measurements of the water level taken in the previously made experiment. Afterwards, the standard deviation was calculated to approximate these uncertainties in these measurements. At last, every value was rounded off to the first significant figure. As to calculate B in, we consider the distance to the water that has been displaced between the first and last measurement and divided it by the time it took the water to get there. Regarding its uncertainty, it was obtained by adding up the uncertainties of both measurements, H. Afterwards, such value was converted to a percentile uncertainty and divided by the percentile uncertainty of time. At the end, both uncertainty and the V in were rounded up to the first significant figure. To calculate the exit velocity, we considered the continuity equation. In said equation, it is said that for continuous flow, the initial velocity times the cross-sectional area of the tube is equal to the exit cross-sectional area times the exit velocity. After solving for B out, we were left with this equation. Afterwards, to calculate the uncertainties for B out, each and every uncertainty, A1 and A2 and B1, were converted to percentile uncertainty. Subsequently, they were added up as a percentage to get the percentile error of B out. Finally, this error was converted to an absolute error and rounded up to the first significant figure. To have better understanding of what we did 2 different graphs. The first one represents the dependence of water level H in the bottle over time. Here, we can see how the water level reduces linearly until it gets to 125 seconds. Afterwards, it changes the way the water decreases. And in the other graph, we have the dependence of the average velocity at the outlet on time. Here we can see how velocity is more or less continuous until it gets to 125 seconds and it drops. When we compare both figures 4 and 5, we can appreciate some similarities between them. At first glance, we can observe that in figure 4, height H decreases linearly for around 125 seconds before a slight curve is shown. Something similar happens in figure 5, where speed remains more or less constant for 1 meter per second for the same period of time before it starts to decrease. Considering that we were using a Marriott bottle, it was expected that the velocity was to remain constant, as well as the rate of change H. Stated in the theoretical framework, the rate of fusion should remain constant while the inlet tube is below the water level. In this case, the fusion rate was constant until the water level was below the lower end of the inlet tube. It is worth mentioning that bubbles were only present when there's a constant airflow inside the tube, allowing us to visually know when there's a constant airflow and when not. After the water level was below the lower end of the tube, bubbles stopped flowing, meaning that the pressure stopped being constant. Therefore, the Torricelli's equation is no longer valid and the outlet velocity is no longer constant. When calculating the outlet velocity by using the Torricelli's equation, we obtain that at this value, it is 1.25 meters per second. After comparing the set value to our theoretical value, we observe that theoretical value lies within the parallel range of the uncertainty of the estimated value, 0.4, 0.6. Although the theoretical value and the experimental value have a discrepancy of 0.35 meters per second, the theoretical value is within the range of uncertainty of the experimentally obtained value. Even when the theoretical value and the experimental value were close enough, a lot can be improved about the experimentation. Given that the uncertainty was 60% of the calculated value, we can take that as an indication that we must be more careful when constructing parallel, as well as with taking measurements. This could help reduce the uncertainty and narrow the percentile error between the theoretical and experimental values.